Okay, welcome to guide sheet number 3 in the conservation laws. We're talking about energy here and kind of comparing energy to work. Again, work is equal to the change of energy. When we talk about energy, we talk about it normally in two forms. Kinetic energy, KE, is the energy of motion, so we're doing something with the energy. Right now we're talking mechanical forms of energy, so we're talking about the speed of the object. The kinetic energy of an object is 1/2 its mass times its velocity squared. The GPE, or gravitational potential energy, often referred to simply as PE because it's the most common form of potential energy that we deal with in mechanical systems, is mgh, where m is the mass, g is the acceleration due to gravity, or the gravitational field strength here on the Earth, 9.81 newtons per kilogram. And h is the height above some zero level. Okay, so first we're just going to see if we can figure out in which situations would these statements work with potential and kinetic energy. So number one, if an object's at rest, it certainly does not possess this form of energy. So if it's at rest, it can't have kinetic energy. Okay, kinetic energy is energy of motion. It has to have a velocity or a speed. So it can't have kinetic energy. Depends upon mass and object height. That's going to be your potential. Height is based on gravitational potential. The higher you are, the more energy you have. The energy an object possesses due to its motion. Again, the energy of motion is kinetic energy. 4, the amount is expressed in the unit joule. Joule is going to be both. So work is equal to the change of energy. Therefore, work and energy must be measured in the same units. So a Newton times a meter, which is 1 joule, are the units of work. The energy stored in its object due to its position, a little hint there, height. If you're talking about height, again, it's GPE. And just because something's at rest does not mean it has gravitational potential energy. It does have to be at some height above whatever your zero level is. So in number 6, the amount depends on the arbitrarily assigned zero level. Again, that's GPE. We have to measure the height from somewhere. Where we measure the height from is really arbitrary. It's up to us to pick our data point. Depends upon mass and speed of the object. That's going to be your kinetic energy. Notice it is speed squared, so speed has a really large impact on the kinetic energy of something. 8, if an object is at rest on the ground and certainly does not possess this form of energy. So in this case, again, that's both. If it's at rest, it can't have the energy of motion, and if it's on the ground, which we're calling zero height, h is 0, so it also could not have gravitational potential energy. If something is sitting at rest on the ground, it's very unlikely that it's going to start to move. Okay, it doesn't have any kind of real energy of its own. If it's sitting at rest on a hill at some height, it may start to roll down the hill. So, gravitational potential energy is about height. Kinetic energy, again, is about motion. Okay, in calculating, a toy car is moving along with 0.4 joules of kinetic energy. Its speed is doubled. Then its new kinetic energy will be. Well, keep in mind that we are doubling the speed. Now, if you square that impact, 2 times 2 means you're going to have 4 times as much kinetic energy. So we're going to go from 0.4 to 1.6 joules. So again, that's a 4-time leap just by doubling the kinetic energy. 3, a young boy's glider is soaring through the air, possesses 0.8 joules of potential energy. If the speed is doubled and the height is doubled, the new potential energy will be 1.6. The speed being doubled has no impact on the potential energy. The height being doubled, if we double the height, we don't have to square the height or do anything else with the height, so we're going to double the total amount of potential energy. Which would always be true of an object possessing kinetic energy of 0 joules. Okay, if it has no kinetic energy, then it must be at rest. It can't be moving. Now, it says, which is always true, it could be accelerating from rest and starting to move, but it doesn't always have to be. It's at rest above ground level. Not always true. It does have to be at rest. It's above the ground, nothing to do with kinetic energy. Moving above ground level, if it's moving, it can't have 0 joules of kinetic energy. So the only one that must be true is that it must be at rest. Kinetic energy is energy of motion. 0 joules of kinetic energy. We cannot be in motion. Which would always be true of an object possessing a potential energy of 0 joules. Okay, it has nothing to do with the speed or whether we're at rest or not. So it's not this one. Has nothing to do with whether we're accelerating or moving. What matters is it must be above the ground. Okay, if it's on the ground, it would have 0 joules of potential energy. If it's moving on the ground, again, 0 joules of potential. That would be kinetic. If it's at rest above ground level, it could be at rest above ground level, but it doesn't have to be at rest. It just has to be above ground level. And it's moving above ground level. Again, the motion part has nothing to do with the gravitational potential energy. So it doesn't have to be moving or at rest. It just has to be above whatever we're calling 0, which here is the ground. Okay, a couple of quick calculations. Calculate the kinetic energy of 5.2 kilogram object moving at 2.4 meters per second. KE is going to be 1/2 of 5.2 times 2.4 meters per second. Don't forget to square that. Now, kilograms times meters squared and seconds squared is going to give you joules, Newton times a meter of energy. So this does indeed give us energy. In this case, something to keep in mind, a joule is not a very large amount of energy. Okay, so in this case we get about 15 joules worth of energy. That's not that much energy. 1 joule does not do a whole lot. 7, calculate potential energy, same kind of object, 5.2 kilograms. We're going to need to multiply that by G, 9.8, and multiply it by 5.8 meters above the ground. That time we're at about 296, which 2 significant figures pretty much rounds off to, again, MGH, so 5.2 kilograms. I'm going to use 9.8 newtons per kilogram for G. If we round it off to 10, we'll get the same to 2 significant figures. 5.8 meters, and we get just about 300 joules. So you can see significantly more than we had from the kinetic energy up above. Now, calculate the speed of a 5.2 kilogram object that possesses 26.1 joules of kinetic energy. So if kinetic energy equals 1/2 mv squared, to solve that for v, we're going to multiply both sides by 2. We're going to divide by the mass, and we're going to take the square root. Alright, so we're going to take 2 times 26.1. We're going to divide that by 5.2 kilograms, and we are going to take the square root, and we're going to get 3.2 for the speed. And that'll be in meters per second. Okay, so again, kinetic energy, energy of motion. We're talking mechanical forms of energy right now. Gravitational potential energy, energy of position. The higher you go from your 0, the more potential energy you're going to have. And we'll pick up with that on the next video.